because that part
Can you get it to work?
Hey guys, I'll just take this chair.
Can you give me that? You need that. I know, but I do.
Oh, sure. Alright, we're going to get started today on motion planning. Specifically, we're going to talk a little bit about the primitives of motion planning, like how do you set up the problem, what are the ways to come up with a solution, and then we're going to go to planning on graphs and talk a little bit about the I'm sure you've seen this before, like Dijkstra, A-star, BFS, DFS, so all the basic search algorithms on graphs, and how we can sort of represent the motion planning problem formulated as a graph search problem. And in the continuous planning space, we're going to look at very specifically one example. So RT, the randomly rapid, I forgot the order, but like random rapid expanding trees. So we're going to look at that very specifically because you're going to implement that on the car for the lab. So that was one of the motion planning algorithms where it's easy enough to implement, it's going to run fast enough to actually run on the car. Right. So the motion planning problem as an overview. So basically there's a few knowns that you're given. So basically you have a robot with some configuration space C. You have a set of obstacle space for C ops. You have an initial configuration of the robot and a goal configuration robot, and you possibly have a cost function describing how much each move your robot takes is going to cost, whether it's energy, whether it's time. And the goal for motion planning is that you want to find a path so that basically it's a continuous function that takes you from the initial configuration of the robot to the goal configuration of the robot, avoids obstacles on the way, and an extra requirement on top is that you possibly want to find a minimum cost path. So you might want to get there fast, meaning that you want to minimize the time that you're traversing the path, or you want a low energy cost. See, like if you have a car that you're trying to save fuel or charge on, you want the minimum energy path. So those are like the very basics of the motion planning problem. So there are two keywords that you can sort of think about when you're coming up with a new motion planning problem. So one of them is completeness. An algorithm is complete if it terminates in finite time. So basically it means that it doesn't run as long as it wants, and it returns a solution if there exists a solution. And if it returns nothing or failure if there is no solution. Another keyword is optimality. So an algorithm is optimal if it returns the minimum cost solution. So this is like a very, very rare occurrence when you can actually find the absolute optimal path. There do exist complete algorithms for motion planning. They usually require runtime with like increasing number of degrees of freedom depending on your robot. Also the runtime increases exponentially fast. So none of these algorithms are usually practical. You don't have an infinite amount of time budget to come up with a motion plan and execute because you have some real life constraints. You can't just let the robot run forever. so they are not implemented, basically. All the practical algorithms that you will actually see people put on robots, it relies the completeness guarantee or the optimality guarantee in some way, so that they live in the middle ground where it runs reasonably fast and it have some level of guarantee for completeness and optimality. So it's not so bad, it runs. The runtime is okay, it's not too slow. All right, any questions so far? All right. So one way to think about how to represent a motion planning problem is basically converting the problem, the formal problem that we saw before, like a continuous function that takes a robot from the initial configuration to the goal configuration. You want to convert that problem into a search algorithm. So it's usually like the final step of motion planning. We'll go over multiple ways to construct these kind of representations. So like there are grids where you're basically converting a continuous world into a sort of, actually all of these are kind of abstracting your continuous world into a discrete representation so it's tractable. So we'll look at grids, graphs, and trees specifically. All right. Is anyone familiar with the concept of occupancy grid? I think Matt went over it during the cartographer lecture, so you should have some idea about like what this thing is. So the goal here is we want to discretize a free space into a grid. So if you think about a grid, basically let's think about all of these problems in 2D for now, because we're dealing with a pseudo 2D problem. So for a plane, how did cartographer do that? Can anybody answer that? So like specifically, how did they discretize the free space? Anybody? It's very simple, right? It's basically they divide up, they have a certain size for a grid cell or squares, and you're just dividing up the 2D plane into multiple grid cells, right? Or what we call an occupancy grid. So it's kind of hard to see here, but you can sort of see there like these little squares that divides up the whole space. So a grid cell, you can represent a free space if it doesn't overlap with any obstacles. So this is the case where you're using a binary representation for a grid cell. So a grid cell could either be 0, meaning that it's free, or 1, meaning that it's occupied. In cartographer's case, the cell, if you remember, it doesn't really contain a binary value. It's a probabilistic model, so it has a number between 0 and 1, meaning that what are the odds of that cell being occupied. So if you see like 0.8, it's very possible that the cell is occupied by free space, and if it's low, that means it's probably free, but you're not sure. Any questions so far? All right. So yeah, a little zoom in version, you can see all these little squares, and the red ones meaning that it's occupied. So we'll go into a little bit more detail. For example, you can come up with your own implementation of occupancy grid, right? It doesn't have to be a single layer. So in this case, you can use a lot of different layers to represent, to give like objects in the environment a meaning. So as you can see here, we have basically 3 colors. You have the black, you have the red, and then you have the green, the blue. So in this case, this is just a very simple example. The environment layer is basically the information that you know before you even started doing motion planning. So basically, if you remember, after you run cartographer, you'll have a map, and then that's going to be the map that you run everything else afterwards. So you can probably already store some information from the map that you don't need to change during this motion planning process. And then there's the static layer, which means that it's information that you're seeing from your sensors. Either it's a camera or it's a LiDAR that basically from those you can tell that there are objects in the environment that you didn't see in your mapping phase, but you know that it's been there or you've seen it multiple times during your motion planning. So you could probably put it in a static layer, meaning that I didn't see it before, but it has been here for a while. And then you have the dynamic layer. So in this case, we have another race car. So that means that in this layer, you can put in stuff that you only see for like 10 frames and you didn't see it for the next 10 frames. So it's going to be a moving layer where the cells can change value every time you do the motion planning again.
Would those also be like a probability style thing, like a cartographer? That would just always be like if you see it for the dynamic one and so on.
So the question is like, does this need to be a binary case or a probabilistic? So this is more on how you implement it to your liking. So you can keep all the layers probabilistic, meaning that it's storing a number between 0 and 1. And maybe for different layers, you'll have different ways to update that probability. Yeah. Yeah.
Cartographer also does this differential layering.
So the question is, does cartographer has this layering mechanism? I don't think so.
Because it does remove the dynamic obscurantism. Like it doesn't capture.
Yeah, so that is the way that they're updating the odds that you're seeing in occupancy. So if you don't see it, during your mapping phase, if you see something moving, you probably don't want it in your map. I don't think it has a multi-layer. It might. I'm not sure. All right, so now that we have converted our environment into a discrete space, so basically we're representing this as a grid world, basically. So no matter where you are in that grid, so you're basically converting from X, Y to row column. You can think about it that way. So your X, Y could still be continuous in one grid cell. So that means that one grid cell represents infinitely many X, Y values. All right, so if you're planning in this space, your input will just be your discrete map with cell labeled as occupied or free. So in this case, we're still not considering dynamic things yet. So your action space is basically what cell the robot can reach from my current cell. So like for my current cell, there's a set of neighboring cells that I can reach at the next time step. And then your cost function is going to be what is the cost if I go to, say, like this neighboring cell versus if I go diagonally to another neighboring cell. So in this toy example, we'll have the blue car as the start state and the orange car as the goal state. So the output of the algorithm is just going to be a list of cells or like a path where you traverse. All right. So now that we have a discrete representation, we can sort of talk about how do we do a search algorithm on these. Right. So if you think about it, you can basically represent this grid world with a graph model, right? You have, for example here, for a 4-connected model, you have green as the current node, and your neighboring nodes are basically these 4 gray ones around it. And you can construct a graph by having node and vertices. So just a recap on what graphs are. So it's just ordered pairs of vertices and edges. And then the edges are basically a 2-tuple for two vertices. You can represent that as either directed or undirected. Directed meaning that you can only go one direction on that edge. Undirected means that it doesn't have any constraints. It could also be weighted versus unweighted, meaning that you could model your cost for each action basically with a weight on the edge. So we have this, if you remember from your basic CS algorithm class, we have this concept of best first search. So it's meaning that you're choosing the most promising node in your next action according to some rule, right? If you're representing the world as a graph, there's several ways that you can choose this heuristics. So, question, do you remember what the algorithm's called if you choose the shallowest nodes first? Yeah, so BFS. Is there any guarantees and downsides for BFS? Anything else?
Guarantees that it will search certain states.
Yeah. And downsides?
High dimensions.
Yeah, it guarantees shortest path, but it's storage intensive. Basically, you're exploring a lot of nodes to come up with a solution. What about deepest next? Yeah, so depth first search. And same, any guarantees and downsides?
Same thing.
Is it the same thing?
It's longer to search.
Does it guarantee shortest path? Right, so you kind of have the flip side here where if your goal is deep, you can get to that point fast, meaning that you're storing a lot less nodes, but there's no optimality guarantee. What about cheapest next?
Oh.
All right. So basically, you have these. So for example, uniform cost search. That means like every single action have the same cost. It's kind of similar to BFS and DFS. Or this is basically without any heuristics. You're just doing all directions. So also there's Dijkstra's and A-star, which we'll talk about next. All right, Dijkstra's. So basically Dijkstra's, this is just going to be a review. Please point out if there's any mistakes that I made in the slides. So for Dijkstra, we have this concept of running cost. Basically, it's the lowest cost to reach, say, like a given vertices, a vertex V. So for a given vertex V, you have a running cost, which is the lowest cost to get to that vertex from the start node. So the way that Dijkstra prioritizes the next node to pick is to pick the node in the frontier or your unexplored set that has the lowest running cost. Right. So here's basically a pseudocode for Dijkstra. So the way that it runs is that you first create an unvisited set, or in some contexts referred to as the frontier. So for all the vertex in the graph, you basically start by assigning the running cost for all the vertices to infinity, and then set the successor to all the vertices to none or undefined, and then you add all the nodes to your frontier. So while your frontier is still not empty, meaning that you're not done and there's still nodes to explore, you're picking out the vertex in the frontier set with the lowest running cost. You remove that node from the frontier, and for each of the neighbor vertices of that current node that you're picking out, you're going to basically update, you're going to find an alternate running cost by adding the running cost of vertex u here with a cost between these two vertices that you're exploring. So if your alternative cost is lower than the current running cost for B, basically you found a shorter path or a lower cost path. So you're updating that and you're adding the new vertex in the frontier U as your successor for B. And you're running this algorithm iteratively until you've reached your goal vertex. Basically, if your U is the vertex, you terminate, or you've explored everything and still basically you terminate when you find the goal state. All right, so a toy example that basically we're trying to find the shortest path on from a node to between two nodes on the graph, right? So for example, we're doing from Pennovation to Van Pelt here. We're gonna abstract this into a graph, basically construct all the edges between vertices, and then we're gonna give each edge a cost. So these are just arbitrary numbers, but it's kind of based on length of the edges. So this is another way that you can sort of play with this. The construction part of your problem is that you can decide like how to define these costs. All right. So now we have this graph representation. All right, we're going to go through Dijkstra. So basically, currently you're exploring the two neighboring nodes, right? Say you have running cost for V1 is 7, and for V2 is 10. So you're going to go for 7 as your next node to explore. And then after that, you go to V1's neighbor, and you see that for the running cost for chop is going to be the previous running cost for your previous node, plus the cost for that edge between the two nodes that you're exploring. So 11, 12, we're going to pick 11. Actually, no, I made a mistake there. There's another one you're still exploring which has a lower running cost than either two of those. So you're going to pick V2 here instead. Is that clear? Right, so you didn't just get rid of that when you don't pick it, it's still in your frontier. So now you're exploring two more nodes, and you have 14, 18, 11, and 12, and you're going to pick 11. So now you see that Levine is visited again, but since the running cost for Levine now is 11 plus 6, which is 17, which is lower than the original one that I got, so you're going to update the running cost for Levine. So now you're picking between 12, 17, and 14. You're going to pick 12. All right, you're going to keep doing this until you reach the goal, and basically you'll also have a cost, lowest running cost for the goal. All right. So now we're jumping to A star. A star is very similar to Dijkstra, but it also has an extra heuristics value or a heuristics function that you use to estimate the true value for the next node and decide which node is the best to pick. So you're estimating the running costs still. So that part is the same from Dijkstra. You also add in another function which underestimates the goal to reach from that node to the goal. So that is what we call the heuristics function. So there are two sort of property for a heuristic function. It's very problem specific. That's basically like you can define the heuristic function differently based on how you set up the problem. So heuristic function needs to be admissible, meaning that it never overestimates the actual cost to get to the goal from that current vertex that you're evaluating. It also needs to be consistent. This is basically the triangle inequality, meaning that you're for every vertex that's not the goal vertex, your heuristic for that current vertex needs to be less than or equal to the cost between node V, the successor of V, plus the heuristics of the successor of V. So also another side note, consistency implies admissibility, but not necessarily the other way around. So it's a very similar pseudocode for A star. It has basically the same structure, overall structure of the algorithm. The only place you're changing the basic Dijkstra to A star is when you're picking out the next vertex, basically to explore in your frontier set. You're picking using this FU here, meaning that it's the sum of the running cost and your heuristic function instead of just the running cost. Yeah.
When calculating your alt, change to what's the heuristic?
Oh, it should be FU.
Or FU is a GU? Or no, you usually do a plus HU at the alt is the same thing.
Oh, the alt there. Yeah, yeah. I'll fix that when I upload the slides. All right, so we're gonna see like a toy example for Dijkstra and A star. You can kind of see the difference between these two. So in this example, the cost for each action is, I believe I did uniform for going from one grid cell to a neighboring grid cell. And then the heuristic I used in A star is Euclidean distance, basically. All right, so this is Dijkstra, and you can kind of see with a uniform cost, it's spreading like a fire on grass. So it's exploring this. So basically, green is frontier, the red is the visited set. It's going to expand like this until it reaches the goal set. All right. And then for A star, you can see if you have nicely constructed heuristics, it's much faster than running just Dijkstra. Alright, so we're going to go back to the two concepts for completeness and optimal. Alright, just a reminder, basically complete means that the algorithm terminates in finite time and returns a solution when there is a solution. Optimal is that it returns the minimum cost solution when a solution exists. So we're going to ask the question that in our toy example on the grid world, is A star complete? Basically, does it return a solution when there is a solution? Yes. Yes. Is it optimal? Yes. Yes. What were you saying? Yeah, exactly. So assuming that a heuristic is admissible, if you picked a really bad heuristic, it wouldn't be optimal. So is Dijkstra on the discrete grid complete and optimal? Let's go from, like, is it complete?
Yes.
Is it optimal?
What is optimally like one shortest path? Or
Lowest cost solution.
yes.
Right, yeah, because it's a special case where your heuristic is basically 0, which underestimates the actual cost to go from a vertex to a goal. All right, now we're going to switch gears to go into the continuous world, where it's a lot more fun. You're not really doing it in a toy example, you're going to actually start doing it on a car. So basically what we expect from the end of this lab is that you'll be able to do something like this, right? You can plan a collision-free trajectory through clutter space, even when the box is just thrown at you, you don't know what was there before, and it's basically a dynamic object in the world, right? So we're going to introduce this concept of configuration space versus workspace. If you've taken 520, the mean 520, you've probably seen this before. So basically, configuration space is the space where a complete specification of the position of every point in the system lives, right? For workspace, it's the space where your robot is actually manipulating it. So in an ARM robot's example, your configuration space could be, let's say, the angle at every joint, right? The workspace could be your position, the 3D position of your end effector in the real world. So as you can see, the configuration space might be, and usually is, in a different dimensionality than your workspace. And a side note is that even without obstacles, not all workspace coordinates are attainable. Basically, for an arm, you have some sort of range that you can reach, and you have some sort of angles that your arm can configure itself into. And for a car, since it's non-holonomic, it can do stuff that a Roomba robot can do, for example. So in our race car context, you can sort of set up this two spaces to your liking, right? For configuration space, you can set a lot of different stuff that defines your car's current configuration, right? You can set the 3D pose, you can even put in linear velocity, angular velocity, and if you want to go even lower, you can even put in like the motor RPM or the torque on the servo motor. And the workspace is pretty simple. It's just going to be the 3D pose of the car. Right, so the challenge that comes with defining these two spaces is that once you go higher dimension in your space, in the space that your algorithm is operating on, the runtime, the complexity increases by a lot. So in our context for a race car, you also want the planning algorithm to be very responsive, right? It needs to react to the change in the world so it doesn't crash, because imagine if you're running at like 10 miles an hour, it's really hard to say for comparing running at 30 miles an hour versus a Roomba robot, the time that requires that you react to an obstacle is a lot shorter when you're going faster. You also have potential dynamic obstacles. So in this case, in the last race of the semester, we're going to have head-to-head racing. So you have to come up with ways to basically avoid another vehicle, which is also traveling at a pretty high speed. And lastly, you'll have motion constraints. As I mentioned before, our car is non-holonomic. There's certain things that it basically cannot achieve. So one of the examples we have here we're going to introduce is RT, rapidly exploring random trees. So as you can see in the picture, in one iteration of the algorithm, it kind of explores the space with a tree-like structure. Actually, any questions so far? All right, we're going to go into another pseudocode. So basically, RT, you're living in tree space now. So you're trying to construct a tree in your world that explores the free space around you. So in the beginning, you're going to set up two sets that represents the tree. Basically, your vertices set and your edges set. In your implementation, you'll have the freedom of choosing like how you want to implement the tree data structure. So the basic idea of rapidly exploring random tree, right? You see there's the name random in it, right? So there is randomness to the algorithm. So the randomness comes from, first of all, you're basically sampling for a point in the free space, right? You can randomly choose a point in the space around you, and then you're checking if it's free space or occupied space. If it's free space, you're basically dropping a node there. We're calling it X rand here. Once you've sampled in the free space, we're going to find the nearest node on your current tree that you've explored. So basically this set of vertices and edges. You're going to find the nearest node to that sampled point before that you dropped before. So we're going to talk a little bit about like how to come up with this nearest function. There's different versions of how you define nearest, right? It could be it's nearest in terms of cost. It's nearest in terms of like Euclidean space. There's a lot of options. All right, and then once you find the nearest node on the tree, you're expanding the tree with a steer function. So this is basically extending the tree from your nearest node to your the random point that you sample. So the steer function is also another thing that you can customize. So you're not necessarily connecting the nearest node to the random node that you just sampled. You're probably expanding by some length toward that direction, or you can come up with your own way of creating that edge. So the edge doesn't necessarily have to be a straight line, right? Just for example. And then after you've, yeah?
So is the steer function where you would, if you wanted to like add dynamics to this,
yeah,
you would add dynamics across the steer function?
Yeah, so the question is, if you want to add dynamics to these paths, is the steer function where you would do that. Basically, it's not the only place that you could do it, but it's one place that you could do it. So basically, instead of, because if you think about trees, the data structure, you usually think about straight edges between the two nodes, right? Mm-hmm. If you're operating in the workspace, so basically the 3D space, it doesn't necessarily have to be a straight line. It could be a dynamically feasible spline that your steer function creates. Yeah. Okay. So next, once you've created this new node and the new edge with your steer function, you can check, basically check if the edge is an obstacle free. So this is another place where you can customize this function, right? You can have some way of checking the edge against your occupancy grid, just basically checking it if it's crossing any occupied space or not. If it's free, you can add it to your tree. And basically this is running on some, as you can see, max iter here, so it's some computational budget. We're gonna go, so there are some guidance in the lab handout on how you actually implement it. So there are a few termination condition that you can choose, right? If the new node that you're exploring or the new node that you've expanded is close enough to your goal, you can terminate. So that's another option. All right, so it's another toy example. Same as before, we have the blue car as start configuration. We have the orange car as the goal configuration. So if you can see here, we kind of got rid of the grid world that we were operating in before. So basically that means that RT is kind of operating in between these two spaces. So the sampling step and the steering step is operating in a continuous world. So it doesn't have any constraints on how you can sample the points. But once you're in the collision check part, basically how you're representing the world is in the discrete way. So RT kind of operates in between those two different spaces. Right, so let's say we have the nearest node on the tree is basically where the car starts for the first concept. And then we randomly sampled a point, so I'm going to denote it as a green point, and the new node from the steering function I'm going to put as the blue point. So for every time step, you're basically sampling a new point. So the steering function I'm using here is basically expanding the tree toward that direction up until some distance. So it's not directly connecting it, it's just expanding it. Right, so you'll go through this, and then, oh, this edge is no good. It crosses some obstacles. So so you're gonna, basically in this case, you're gonna discard this sample, you're gonna resample, basically do the same thing again over and over and over, and then you're gonna start growing a tree, and then in this case, I basically have, if the node I'm expanding is close enough to my goal, I'm gonna terminate. And I'm gonna traverse the tree back up, so like you're going from the node that you like, and then you go parent to parent to parent to parent, and all the way back up to the last node that you can explore. So basically that completes a path. Right. Any question on this? Right, so as you can see, like if we don't do any modifications, the path of RT is kind of jagged. As you can see in before, like if you just pick a path out of these, it's really bad. Doesn't have any guarantees that your robot can actually reach those. So for extra credit in this lab, we did put in the paper where RT star is implemented. So if you can, so basically what RT star does is that after you have the path, you're modifying your path to find a lower cost path than this one. So basically the extra credit is that you can implement RT star on top of RT, and then how you choose what cost to use is also up to you. There will be more details in the lab. All right, so as you've said before, some of the modifications that you could use, right? So basically you can modify the steering function to your liking. Right? It doesn't have to be a straight path. You can come up with a spline that the car can actually achieve, and then use that to represent your edge between the vertices. And also you need to design a function to check collision, right? So basically, you might not just want something that checks if your actual trajectory crosses an obstacle. You might also want to check, right, your car is not a point mass, right? For example, you might want to add size to that point. So these are all things that you could do in your lab. There's also different sampling strategies. So as we said before, you're randomly sampling points in the free space. So that kind of, that sampling, it doesn't have to be uniform, right? You could sample it uniform like this, evenly in the free space, or you could have some strategy where you bias your sampling towards the point you actually want to go to. So you can sample more often near the go point, or if you can come up with other bias functions. Right. Any questions? Yeah.
So this something is global, and the steering function tells us a new node to sample, right? The steering function gives us a new node to sample. Is that how it works? Because you're getting an X new as the return. one.
Yeah, so it's constructing, so the question is, basically the x new and x rand is not the same point.
Okay.
So the steering function doesn't necessarily use the x rand. You're basically sampling for a direction.
For direction.
Not necessarily direction. You're sampling a point, but your steer function could expand that toward that direction, expand the tree toward that direction. Right? If you're going to think about it, you might be sampling from a very a point very far from your current tree. If your expand function or steer function just connects the nearest point to that point, you're going to have a very long edge across the whole map. You probably don't want that because it takes time to check, right? If you're sampling on that edge to check if there's any collision, that's going to be an outlier because it takes way too long to check that. So you could do that, but you usually will want some constraint on how you could expand the tree.
Okay.
So you're adding the x new from the steering function to your vertice set instead of the random sample point.
Okay, but the random sample point gives us like some place to start.
Yeah. So you have some rules like, okay, I sampled this random point, and then I should do something about it.
Foot in that direction.
Any other questions? Yeah.
So RT star is after you already have like a completed path.
Yeah.
And then, yeah, you sample more and then you just improve it.
Yeah, so you have some rules for what an edge costs, and you modify the path based on those costs. So in general, it's going to give you like a straighter edge. It doesn't have these like really sharp turns.
So in like real time, we're doing like short paths, right, generally?
So for the lab that you're implementing, actually that's a good point. So we're kind of not using RT as like a global planner. So usually in other papers that you see, you're using the RT star to explore unknown spaces. So you're basically trying to gather information about a space. So you're keeping one tree, expanding it all the way throughout the time steps. But in the lab that you're going to be implementing, you're basically expanding a new tree every time you get new information from the sensors. So it's more for a local planner for obstacle avoidance. Yeah. All right. So RT is probabilistically complete, right? Meaning that because it's random, there's not going to be any guarantee on completeness, right? So the probability that the algorithm returns a solution when one exists, it's going to approach to 1 when your number of samples increase, right? So RT, the basic RT is not optimal. That's due to the random sampling. There are variants of RT to provide a solution that keeps the cost in mind. So as I mentioned before, RT star is one of them. So we're gonna, any questions? Yeah.
Yeah, I have one more question on this also. So when we're doing this obstacle free step, I think we have to sample all the nodes in between. So do we add those in between nodes to the V and E sets as well?
You're not explicitly creating new nodes. So the question is, during the obstacle-free function step, do you create new nodes along the edges that you're checking? So the answer is yes and no. So a very simple way to check if the edge has a collision with the world is you're basically picking points on that edge in real world, and you're basically checking every point. Oh, is this occupied? Is this occupied? Is this occupied? So there could be a way to like still create a new expansion instead of throwing it away by checking. Okay, this is the last one. So you're going from one direction, and then you hit an obstacle. You hit an occupied point, right? You're going to go back and say, okay, this is the last one that didn't hit any obstacles. you could probably do something about it instead of throwing it away, right? You could probably create a node there and expand that instead of creating an expansion that goes all the way across the obstacle. So that's kind of your choice.
That would slow down your program. Like, the more nodes you have, the more you check in your nearest function. So that would be good.
Yes.
That's why we wouldn't add it.
Yeah, so it's kind of like, do you want to increase your nearest search, or do you want to have, like, because that might give you a better chance of finding a path. Yeah?
How would you switch between local planner and global planner?
So the question is, how do you switch between global planner and the local planner? So in our case, at least the way that you're implementing it in the lab, your global planner is going to be basically a waypoint that you select, a list of waypoints that you select around the track. Because in our context in racing, you basically have a loop and that you're going around and around and around. It's really hard to define like a start and a goal. So basically, like globally, it's really hard to define a start and a goal, right? Because you can imagine I can put the start right next to the goal at the finish line, but you really want to go all the way around to that goal. So what we set up is that we have, in the local planner, or RT, in every frame you have a current goal. So kind of similar to how peer pursuit works. So you're kind of expanding the tree toward the current goal. And then you're expanding a new tree every frame. Yeah, is that clear? Any other questions? All right. So, reading assignment. This is basically a paper on the analysis of basically optimality and completeness of these sampling-based algorithms. It's a really good paper if you want to read it, the whole paper. It's yeah, it's going to be really good. There's some really good insights in it. So sections 3.1, 3.2, and these three algorithms are basically how they modify RT to become RT star. And then the lab handout is already on GitHub, updated. So you have a written assignment. Basically, you're playing that grid world game with Dijkstra and A-star, and you're going to write out the expanded set and the final path. And the next step is that you have to implement a simple occupancy grid on the car. So basically, you need to keep track of what is the current occupancy grid of your world. So this could either be a local one around the car and moves with the car, or it could be a global one that covers the whole map. So the idea here is that you're taking information from the laser scan. You could put the points that you've hit into the map, in the map frame, and you can create an occupancy grid based on that. So this is needed because you need a way to check with collision in your next step, basically RT. As I said before, you're going to implement RT as a local planner, so it's going to do obstacle avoidance, and RT star is extra credit.
This is the
Yeah, this is
I thought
due on March 18th, so this is out. March 30th, sorry. Yeah, so peer pursuit and race 2 is on March 18th. And basically, you have a little bit over a week after that for RT. Yeah, so we're just assigning these early so that you can get the whole spring break. Yeah. So start early. Yeah.
Oh, I was going to say, would it be beneficial to implement RT for the race?
It's not necessary for race 2. As you imagine, if you just have RT, it's probably not going to be, because we're not going to have any obstacles on it.
Oh, okay.
Yeah, so it's probably not going to be faster than peer pursuit.
In the previous slide, said we have to implement an occupancy grid.
Yeah.
So, that's when we global, won't that be kind of like doing some?
Not exactly, because you're already localizing. This is just keeping track of where all the obstacles are, or like where all the points that the laser scan hit are.
But
It's not providing you with any localization information, right? It's just that you basically you know that there's something there that you've seen before.
But how do you know that we're in the same place, like the same part of the
You're using part of the filter to localize it.
So do we use information, do we use an Hongrui build?
Yeah.
The particle for now?
Yeah, so that's the base that you have.
Okay.
And then any new information you get from the laser scan, you can put it in the occupancy grid.
Okay, so it's like only mapping.
Yes and no, because your information, your localization is from particle filter, not from this building process itself.
But we're adding information to our map.
That depends on your implementation. So it could be a local area around. It could also cover the whole building. It's your choice. That's it. Yeah.
So when you say local